Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 25, 2025, about 2 days ago. The striking result is a visual SLAM system that fuses feed-forward Pointmap regression with inertial sensor IMU and global navigation satellite system GNSS data to deliver metric scale tracking, cutting absolute trajectory error from tens of meters to single-digit meters on Kitty 360 and staying robust through 100-second GNSS outages. The paper is titled MASt3R-Fusion, Integrating Feed-Forward Visual Model with IMU+GNSS for High-Functionality SLAM. And as we'll see later, the results are really impressive. It marries dense two-view point maps with a SIM3 to SE3 factor graph, enabling real-time sliding window tracking and global loop-closed mapping. Also, the author shared a GitHub repo with a concise README describing MASt3R-Fusion, its multi-sensor SLAM pipeline, and features like full view depth, loop closure, and real-time sliding window tracking. You will find early evaluation figures and assets, auto-calibration notes, and an ETA for code release in October 2025. Code isn't posted yet. Alright, the repo details were sketched already. Figure 1 shows the full pipeline at a glance. The left section depicts the feed-forward point map prior that produces dense associations across views, which supplies rich 3D structure. The middle block integrates SIM3 visual constraints into a metric scale SE3 factor graph with IMU, GNSS, and loop closures. The right map visualizes cross-frame association angles and suggests operation on long sequences using about 8 GB of GPU memory. Alright, the previous figure introduced the pipeline. Figure 2 shows how the system runs in two coupled stages. The top real-time band ingests images, initializes frames, performs tracking, and matches frames, while local optimization fuses inertial data and marginalized information. The bottom global stage adds loop detection, dense frame matching from the feed-forward model, and global optimization with satellite positioning factors. The map frames block stores keyframes, so tracking and loops stay consistent over long runs. So the previous figure sketched the runtime stages. Figure 3 shows the two-view feed-forward model at the core. The left encoders turn each image into feature tokens. The center decoder fuses those tokens and predicts per image outputs. The right panels deliver two 2D to 3D point maps in a shared iframe, plus descriptor maps and confidence. These dense scaleless point maps enable reliable cross-frame matches, which later fuse with inertial and satellite cues for metric scale. Well, the previous figure introduced the feed-forward core. Figure 6 shows how poses and constraints are organized in the sliding window. The top row depicts camera poses in SIM3, which capture scale changes and connect adjacent frames. The middle row converts those into SE3 plus scale so visual constraints align with metric sensors. The bottom chain tracks IMU pose with velocity and bias, and red squares indicate factors that enable probabilistic marginalization for stable real-time optimization. So, Figure 6 organized the sliding window. Figure 9 compares trajectories on Kitty 360. The top row without loop closure shows several baselines drifting from the dashed ground truth, while the red MASt3R-Fusion path stays tightly aligned, especially through sharp turns highlighted by the insets. The bottom row with loop closure contrasts green orb SLAM 3 and red MASt3R-Fusion, which both correct drift, yet the red path matches the dashed ground truth more consistently on long loops and intersections. So, Figure 9 contrasted trajectories. Table I reports relative pose errors on Kitty 360. The table lists translation error TREL in percent and rotation error RREL in degrees per 100 meters across sequences. MASt3R-Fusion delivers the lowest translation error on most routes, with values near 0.5 to 1%, while DBA Fusion is the closest runner-up. The visual-only MASt3R SLAM shows very large errors, which underscores why inertial fusion stabilizes metric scale. Okay, table I summarize relative errors. Figure 15 presents horizontal position error over time with GNSS-RTK integration. The top panel shows large spikes for GNSS-RTK and VINS fusion, while M fusion with loop holds near 0 and posts a root mean square error around 0.21 meters. The bottom panel repeats the pattern with an even lower root mean square error near 0.094 meters. Loop closures clearly suppress residual drifts, which keeps absolute positioning stable. Alright, two takeaways stand out. Fusing dense feed-forward point maps with inertial and satellite cues via a SIM3 to SE3 factor graph delivers reliable metric scale tracking, and loop-aware global optimization reaches decimeter accuracy while riding through long GNSS gaps. The broader implication is practical: real-time slam across tough scenes. That is it for the AI Research Roundup. I am Alex. Thanks for listening.